We've got 1165 newtons over, and then we've got the it's 10 millimeters times 4 millimeters there. Okay. So 1165 over, well, 10 by 440, isn't it? So I've got 21.1 Newton per millimetre squared.
21 or 29? You said 21, you wrote 29.
No, well, I said, yeah. Yeah.
Okay.
Right,
just checking.
Yeah, 29 is 29, I've got 29 on here.
Okay.
So I think I'm talking into the board maybe. Right, so, and then the other one is 877 newtons over, I'll just write it out conventionally for you. That is 21.9 Newton. Okay. So you can see there with the plastics, if we start to shock load them, or we load them up quite fast, they actually will exhibit a higher strength, but they will fail. Sometimes with some little degree of toughness, other times they will fail very brittly. If it's acrylic, then of course that's a very brittle plastic, and you'll snap it. Okay. By the way, acrylic's got a much higher strength than this because it's an engineering polymer. So, but this stuff is quite big because it's only about under 30 megapascals. And again, the problem with plastics like HDP is it's not that tough. With plastics, the toughness is usually far more important than the strength. Okay. Because we've all probably experienced breakages with plastics. Whether you've had a car accident and you've had someone run up the back of you, or you've bought something, a Hoover or something like that, and then you've cracked the end of the skirting boards. Or, we've all probably experienced plastics failing on us, and you had that term cheap plastic, and that sort of was around in the 70s when plastics were very brittle. They have improved now actually, so they are getting better. Okay. So all we've done so far today is look at tensile testing, okay? But what happens if you're doing some heat treatment and you want an idea about the quality of something? You want to know whether or not it's been heat treated properly, okay? There is another test which you can do, and that is a hardness test. And this is probably one of the most important quality control tests you can encounter in engineering, okay? And whenever there's a sort of an issue with quality, or maybe there's been an accident or something, one of the first things you do is do a hardness test, because that is a bit like a blood test. Okay, it's either going to be healthy and in range, okay, and you've got to do a few of them. You can't just do one. You should do it over the area. It'll take about 5 or 6 readings. So it's either going to be normal and fine. It's going to be borderline, and you've got to say, hang on a minute, do I need to do some more testing, some other methods to start looking at it? Or it's completely abnormal and you're in trouble, or well, it's not so bad if I suppose if it's a specimen in the blood test, but if it's abnormal, then something's definitely up, and you've got to do further testing and try and get to the root cause of it. Okay. So that's what I like to, the analogy I use for that. So what we've got here, I don't know what this is. It's a higher carbon steel, but it's been heat treated. Okay. So we've got one that's been same material, one that's been quenched in water and one that's been quenched in oil. Okay, now, I don't know if you've done anything on heat treatment at all. Have you done anything on heat treatment?
You have done a bit, guys. We did it last week.
So you heat the metal up to quite a high temperature. If it's any kind of steel, it's going to be over 800 degrees Celsius, about 900 degrees, 850. And then you're going to plunge it into either water, oil, brine, or something like that, and that will harden the material. We do it here, by the way, but I haven't got enough time today to do it when I can't get you all in the heat treatment lab anyway. So this one's already been done, and so this is called the Rockwell test. Okay, and this one you'll find in a lot of workshops and things because you get a direct readout, which is quite good. So all I'm going to do, I'm going to look at the water one. Okay, get it under there, and I'm operating on C scale, and I've got to actually wind this round to the thing goes on to set, because that's the 0 mark, and just wind it around. So now it's in position, ready to do the test. Okay. So all I'm going to do is pull that lever back and then pull that back there, okay? And that's given me a Rockwell C scale of about 68, okay? So we can say that the Rockwell
We've got a Rockwell machine.
Have we?
hardness, okay,
I think
the
it's working. Someone
water
decided to take it to pieces last year. But,
quench
I think it's working.
is 68, and that's Rockwell C, that's what we write. So the R and the C tells me it's a Rockwell scale, and it's Rockwell test, and it's scale C.
A bit more than that one as well.
So we'll take that one off. Now we're going to look at one that's been done in oil, okay? Now, what's important about this is that the quenching medium is got to obtain. You want to obtain the right structure in the material, because when you heat treat it, you change the structure inside the material. Okay. Now, I always use the sort of burger and lamb roast thing with this. If you take a material and it's very, very small and you quench it, you've got a good chance of securing that structure right across the material. So that means it's going to be reliable, isn't it? But if it's too thick, then you might not heat treat it. So again, if you cook burgers from frozen, you should be able to cook them fine. If you chuck a lamb roast in the oven for frozen, you'll probably die some to death, because you're going to get food poisoning, because you're not going to cook it. It'll be cooked on the outside, but it ain't going to be cooked on the inside, is it? Okay. So obviously that's why you've got to defrost your lamb roast or whatever you're doing, and then cook it through. Okay. So with this, if it's too thick, it's not going to heat treat properly. So this is an oil one. Okay. So an oil is a less severe quenching medium than the water. The water's more severe. Okay. So again, I'm going to bring it up to set. And that one's only 50 Rockwell C. So oil quench. Okay. So you can see there, this shows that the theory is right, because the oil quench is less, the material isn't as hard because it's had a less effective quenching.
So it's cooled down slower.
Yeah, yes, the rate of cooling is slower. Now you might say to me, well that's okay then, because why don't you just water quench it? You know, if this is a problem and it's not quenching properly, then why don't you just water quench everything? Well, the problem is, when you quench it, the thing undergoes a lot of distortion, okay, geometrically, and that can actually cause cracking. So if you quench it too severely, you'll start to crack the thing, and it could fail. You know, you put stress concentrations in there, and any shock loading, it will fail without warning. So you want to quench it so that you get the right structure in it, but you don't distort it too much. That's why you've got different quenching media. So that's a hardness test. There's lots of different types of hardness tests, and it's because you've got different sorts of materials, different ways of obtaining it. That's what you'll find in the workshop, and usually a standard one, okay, but it's not the most accurate. The one next to it is the Vickers, and that's more accurate. I've actually worked with people who do this, and they're a bit naughty, because if it's Friday afternoon and they're quality controlling, and it's just outside the spec, what they do is they sort of lean on it like that, and it just gets it in the spec, and then they can go sign it off, and then they can go home and have their weekend. You shouldn't do it, it's not allowed, but I know it's happened in the past, you know. Okay, I used to work in calibration, so I did see lots of things going on that, you know, saying that they're not, you know, planes aren't going to drop out of the sky because of this, but again, shouldn't be done, but sometimes it's really annoying. It's right on the edge of the, you know, it's one fraction out, and you want to go home, and they just lean on it. So if you're doing an accident investigation or something like that, you can't really rely on this method because it's got error built into it. Well, they all have actually, but this one's got less error, and this is a Vickers, and this one actually goes underneath a, it's a force, you just press that down, and it drives the diamond into it, and that happens over here like this, okay, and then you swing that round there, you look through the eyepiece, and you'll see the diamond, and then you twistle this here, and it brings the shutters together, and you get a number, a Vickers hardness number, and then you can look that up on reference tables, and it will give you an accurate hardness, okay, but this one's more time consuming, but it's more accurate, okay, so, and there are some other ones around as well. So, and hardness testing is still mechanical testing, although in some people they do say it's non-destructive, but it actually does distort it, so I still class it purely as mechanical testing. So now that's great, but what happens is obviously if you're trying to monitor something, like a railway line or an aircraft wing or something like that, you need to check that no cracks are developing in that. So you can't pull it apart because you want to use it. So you need to come up with some other way of testing, and those methods of testing are called non-destructive testing. And I've actually got some bits of kit out here, okay? So I'm going to show you a few bits and pieces, okay? Now let me just, what I've got to do is just boil up the kettle, so I need to unplug that. I'm not making coffee, but because you can't eat and drink in here, but we'll get that kettle on, okay, and I'll just show you the first one. So we've looked at plastics and metals, but what about concrete? Because concrete's really important. Yeah, a few. When we do concrete preparation, we actually, I need to put this on the floor actually for this. This is a standard cube here, so what you do when you do concrete is you make up cubes this shape, and then you send them away and then crush them in the machine. And the load over the area gives you the strength, doesn't it? Okay? So what you do is, when you do a concrete mix, if you're making West Quay or whatever down the road, or I don't know where you've got in Basingstoke, but not there a few times, but the big festival, yeah, the big shopping centre, yeah, I'm trying to think of the music venue we've been to. The theatre, Anvil. Yeah, the Anvil, that's the one. So whatever you're building, something like that, what you do is you then make up your batch of concrete, you make up your cubes, you send them away, and then they test them cubes. But the problem with concrete is it gains its strength over a period of time, okay? It doesn't just become strong straight away, it actually takes a month to gain its strength. And after 7 days, it should have about 2/3 of its strength. But I don't want to crush all what I've built, do I? Okay? So if I built something, and I send my cubes away, and 7 days later they come back and they say, not too sure about this, they're sort of on the borderline. What we can do is we can, there we go. I can use this thing, okay, and this is called a Schmidt hammer, okay. So, named after Herr Schmidt, who I don't really know a lot about. All I know is that he was from Switzerland because it's also called a Swiss hammer as well, okay. And all I do with this is I take the end, that's on a calibrated spring, so all I've got to do is go like that. And what this does is it gives me a little bar chart on here, and it measures the impact energy that the spring, it's got on a calibrated spring, and the rebound energy is given off in the bar chart form. Okay?
Does it affect how hard you do it?
No, because of the spring. So yeah, you obviously don't want to really whack it in, because you literally just hold it down and like that, just do that. Okay? So this bar chart, I then take an average value across here. It's quite hard to see, but according to this, I'm getting around about a number of 32 on here, okay? And if you look at the back, it gives you a graph, and it shows you if you come downwards, you follow the top line. If I go into it from the side, then I follow the middle line, etc. And if I go up, if you're right underneath and you're going up like that, then you look at that one. So if we look at 32 on here, okay, that's telling me that we've got around about, actually it's 32 newtons per millimetre squared, okay? So the compressive strength for this is about 32 megapascals, okay? So we can put Schmidt hammer, concrete, compressive strength, is 32 megapascals, okay? Now you can't use that on its own, but you could use it obviously in conjunction with other things, okay? So I'll put that concrete cube to one side. Now there is another way you can do it, and the new bit of kit we got in yesterday is an ultrasonic bit of equipment, and you can actually pass ultrasonic waves through it, and that again will give you an estimate of the strength of the concrete. Very clever actually. The ultrasonics you can also use to, if you know the speed of the ultrasound waves, like what speed they travel through, you can put an ultrasound probe on one end and put one on the other end, and you can time how long it takes for the pulses to go through the concrete. Now, if you know the speed of sound of the pulses in the material, then you can work out the time it should take, can't you? And if you get a different time, then that means there's something inside the concrete, doesn't it? So it could be some pipes underground or anything, or something embedded in the concrete. So that's quite a good way of using ultrasonics to find out whether or not there's anything in the concrete. Okay. I've got couple more things to show you on here. I'll go and get the ultrasonic gauge now as well. We can use ultrasonics for quite a lot of things.